Hello. Okay, good afternoon. Today we are going to start another topic of isomerization in coordination complex is stereoisomerism. In last lecture we saw the different structural isomers which are present in coordination complexes. Structural isomers are ionization isomer, hydrate isomer, linkage isomer, ligand isomer, coordination isomer, coordination position isomer and polymerization. You are already familiar with this. The second type of isomerism is stereoisomerism. So what is the difference between structural and stereoisomerism? In structural isomerism, the complexes which are differ in a structure or in a arrangement of ligand in their structure, but in stereoisomerism, if two complexes having same molecular formula, but there is a differences of ligand arrangement in a space which are oriented or which are directed towards the central atom called as stereoisomerism. So when we are going to discuss stereoisomerism, that time there are two types of stereoisomerism, geometrical and optical. Geometrical isomerism depends on if any complexes having the two same groups and if the same groups lie or same groups are attached to the central part, if they are adjacent or if they are opposite. But basically we say there is a cis and trans are the type of geometrical isomers. But in coordination complexes we change this phenomenon. In some complexes there is no same groups are present, but complexes shows the geometrical isomerism because shows the different arrangement of ligands. We will discuss in that point. So first we are going to start the stereoisomerisms. So what is the definition of stereoisomerisms? If the complex having some ligands and if ligands are attached to the central metal atom or ion in a space differently, this type of isomerism called as stereoisomerism or called as space isomerism. Okay. So we are going to discuss one by one. So basically stereoisomerism has two types, geometrical and optical. So geometrical isomerism again we divide or we classify into two different types is the cis and trans. So either maybe complex is cis or trans, same as organic chemistry, but in organic chemistry we consider the double bond and here we consider the central atom or ion. In optical again there are two different types, dextro and Leo, dextro and Leo. Okay. So these are the types of stereoisomerisms. So stereoisomerism classified into two different types, geometrical and optical. Geometrical means either it may be cis or trans. Optical has dextro and Leo. So cis means what? If two groups at the same side or adjacent, or here is the opposite. Trans means opposite. Leo means right side rotation, dextro means, and Leo means left side rotation. Basically in geometrical isomerism we see the two similar ligands, if they are adjacent with each other we call these are the cis geometrical isomer. If two same ligands having the opposite to each other, that time we say there is a trans isomer. In case of optical we just see if when the complex in contact with polarized light, that time the polarized light rotate itself. If the polarized light rotate clockwise direction means it is a right side direction, that time the isomer called as dextrorotatory. If the rotation is left or it is a anti-clockwise rotation, the called as Leo. So there are Leo and dextro, it depends on how plane of polarized light is rotated, it is a clockwise or anti-clockwise. You will understand in polarography, it is the chapter number 4 in analytical chemistry. Okay. So this is about the introduction, what we are going to study in given point. It is the stereoisomerism. So here we are going to discuss in detail one by one. So first of all, we are going to start these geometrical isomerisms. Okay, first of all we are going to start geometrical isomerisms. So geometrical isomerisms, again in coordination complexes, basically we are going to study the two types of complexes. The complexes which having the 4 coordination number and complexes having the 6 coordination number. Okay. So 4 coordination number complexes has again two types of geometry, tetrahedral geometry and square planar geometry. So basically geometrical isomerism will exist in the square planar geometry. In tetrahedral the geometry is not exist because the bond angle is different. So here is a plane, that is why we easily identify either the two grooves are same side or opposite side. But in case of tetrahedral it is difficult to predict. So that is why in tetrahedral mostly geometrical isomerism is absent, but in square planar complexes will exist in a geometrical isomerism form. That is why we going to discuss 4 coordination complexes in that square planar complexes and octahedral complexes. So A is the geometrical isomerism. A is the geometrical isomerism. So geometrical isomerism, when we are going to study first the isomerism in square planar complexes. In that point we are going to learn, we are going to understand the geometrical isomerism in square planar complexes and in octahedral complexes. Tetrahedral complexes has absent the geometrical isomerism. So only we think about the square planar and octahedral complexes. So first point is isomerism in square planar complexes. So square planar complexes, that means if matter at the center and the complexes has 4 corners. So these are the 4 corners. Okay. So this is a simple representation of square planar complexes. There is a bond angle is 90 degree, means if two ligands are adjacent with each other. So two same ligands present here or between these two or at these two position or at these two position or these two position, all are cis. Suppose here we are going to number 1, 2, 3, 4. Okay. So 1, 2, 2, 3, 3, 4 or 4, 1, these are the adjacent position, means these are the cis position. But if same ligands at the 2, 4 or 1, 3, these are opposite to each other, that means these are the transpositions. So which are the cis? 1, 2, 2, 3, 3, 4 or 1, 4, and which are the transpositions? 1, 3 and 2, 4. These are the transposition. If two same ligands having this type of representation or this type of positions, that time we say it is a cis or trans. Okay, we are going to discuss one by one. So first of all we are going to start our first type of complex is A2 B2 type of complex. So first type we are going to discuss is A2 B2 type. Okay. M is the metal, A is the one type of ligand, B is the another type of ligand. Means how many types of ligand here? 2 types of ligand, A and B. Both are monodentate because here 2 plus 2 4 coordination number for complex is square planar. So how we represent the geometrical isomers of this type of complex? So suppose we consider M here, if we draw square planar. So for cis we consider AA is the same type of ligand. So AA adjacent with each other, either this position, these two position, these two or these two. You can consider any two position. Condition is both lie at adjacent with each other. If there are AA, we consider B is here, another B is here. So we say is the cis isomer. For trans, suppose A is here, so another A is opposite to this one, B is here, B is opposite. That means both these similar groups, similar ligands lie opposite to each other. That time the isomer is trans. Isomer is trans. So it is a just simple representation, general representation. For that we consider here example PT Cl2 PT NH3 twice Cl2. This example is given to you, and draw their geometrical isomers. So PT is the central metal, NH3 is the type of one type of ligand, Cl is another type of ligand. There are two 2s are given, that means it is a A2B2 type, A2B2. Okay. So we draw the structures. So for cis, both the NH3 group should be lie at this adjacent position. So here is the cis. What is the name of complex? You already familiar with the rules. So it is a neutral complex. We start the name from the complex part. In a complex part, starting from ligands. In a ligand, starting from negative ligands. So negative ligand is chloro. That means here is a dichloro, diamine, platinum, second, because Cl2 minus 2 is equal to 0, here is a 0, so x plus 0 plus minus 2 is equal to 0, that means x is equal to plus 2. So plus 2 is the oxidation state, is the cis isomer, and this called as cisplatin. Yalla mantat cisplatin, which is the medicine or drugs which is used to cure the cancer. So it is an anti-cancer drugs. It is a cisplatin for your information. Write down, cisplatin is the anti-cancer drugs. And how to draw this trans? So both these similar groups lie opposite to each other. If NH3 is here, another NH3 goes here. Cl, Cl. So here is a trans. Nomenclature remains same. Dichloro, diamine, platinum second. So trans, dichloro, diamine, platinum second, nomenclature is same. Just what is the differences? One is cis isomer, another is a trans isomer. So this is all about the first type of complexes, A2B2. Next we move to the another type of complex, B A2BC. That means here three types of ligand. There are two ligands are same and another twos are different. A2BC. Okay. So general representation is for cis both the same ligands, A at the adjacent, B is here, C is here. And for trans isomer, if A is here, the another A goes to the opposite, B is here, C is here. So here is a trans. If you well known the cis and trans isomer in organic chemistry for the alkene, you will understand here also. Okay, cis and trans. We consider here example, same example. Suppose PT NH3 twice Cl and another one is Br. Cl Br. Okay, that means NH3 is the first ligand. There are two ligands are there, one Cl and one Br. If we consider this example, we can draw the structures. And how we can draw the structures? So for cis, the similar ligand is the NH3 at the same side, and here Br is here, Cl is here. And for trans, if NH3 is here, another NH3 goes to the opposite side, Br, Cl, trans. Here is the cis. and you know nomenclature. What is the nomenclature? Here there are two negative ligands, one neutral ligands. So we start the nomenclature from negative ligand. In negative ligand we use the alphabetical order. So bromo, chloro, diamine, platinum second. So cis, bromo, chloro, diamine, मी आता इकडे खाली घेतो, प्लॅटिनम सेकंड, आणि इकडे काय असेल, ट्रान्स, ब्रोमो, क्लोरो, डायमाइन, platinum second. So these are the nomenclatures. So this way, if for the nomenclature, if complex is given this way, you can mention their geometry, their isomerism first, then write their name. So it is all about the second type of complex. Third type of complex we are going to discuss. So in first case, two ligands are same. In second case, there are two ligands are same and others are different. Okay. But third possibility is if complex itself has all different ligands, M, A, B, C, D, means all ligands are different. It is possible. So in that case, is it geometrical isomerisms are exist or not? According to you, or you say yes, there is absent. Why? Because there is no two same ligands are present. But in inorganic complexes, if all the different ligands are present, also shows geometrical isomerism, but their representation is differently. How it possible? So for that, how we draw the structures? So first of all, you draw the first structure, A, B, C and D. If you want to try to another representation, how it possible? So that time you can hold the position of first ligand and just rotate the positions of remaining three. So you hold, or we hold this A remains at first position, 1, 2, 3 and fourth position. We hold this, means in all structures A remains at the first position, we just rotate remaining three. So in that structure, B is at the second position, C at the third position, D at the fourth position. In next, what is the possibility? D rotate here, B comes here and C going here. So this way there is a rotation. So what is the next rotation? A remains there, we hold the position of A, just D goes there, D, B and C. Okay. Again, in third structure, again we hold the position of A, again we rotate another rotation, D is here, comes here, so D, B and the C goes there. If you try another rotation, A hold, and if you try another rotation, A is here, again B goes there, C is here, D is here. This is the fourth. If you look, A and means first and last one are same, identical. That's why this type of complexes shows only three isomers. Only shows three isomers this way. So how it rotate? Just hold the one position. You can hold this one, this one, this one, any one. You can hold one atom, one ligand remains, and just rotate the other threes. You get the different isomers. So these are, this way the complexes has three possible isomers, and here we draw. So we consider here example is PT NH3 pyridine Br Cl, NH3 amine, Py means pyridine, bromo and chloro. Okay. So these, in that given complexes, four ligands are different, so we can draw the three possible structures this way. Okay. So we are going to discuss first is platinum at the center. Suppose here is the NH3, pyridine, bromine, chlorine. Okay, is the first structure. In second, we hold the NH3 on the same position, just rotate other three. NH3, so pyridine shift here, bromine is here, and Cl is here. In next, NH3 remains on the first position, Cl is here, pyridine, bromine. So these are the possible isomers. So three possible isomers in M, A, B, C, D type of complex. So this is very easier. Just focus which type of isomerism is possible or exist in given type of complexes. So identify which type of complexes is given to you, then you can draw all the possible isomers of given compound. Okay, so this is all about the third type. We move to the next fourth type of complex. So in first three cases we saw all the ligands are monodentate. That means all the ligands, 4 ligands are monodentate, either maybe same or different, but all are the monodentate. Some bidentate ligand also if present,